Hey guys, so some people wanted me to go through and give a key out for this. I didn't get through all of it today, so that's what I'm going to be doing. So for question one, they're asking for the rate expression. Now, rate expression, especially when they say in terms of change in concentration over change in time, you know it's always going to be change in the concentration. Let's do nitrogen first. Change into over change in time. Okay, and what else do we need in here? The two things you need to remember are the following: reactants or products. Which one? So, and then also coefficients. So, if it's a reactant, you know that the concentration is going to be going down. Products, it's going to be going up. Now, the rate is always wanting to be positive. You want a positive rate. This is really just for convention. It's the way we've always done it, Jimmy. So we need to flip the products, put a negative sign there, and that's it. If it's a product, or flip the reactant. If it's a product, it's going to be a positive. If it's a reactant, negative. Then the next thing is the coefficients. So basically, you're going to take the reciprocal of the coefficient. For nitrogen, it's 1. 1 over 1 is 1. I don't even need to put it in. We can just leave it like this. But if we have something like the next one, hydrogen, H2, with it's a reactant, so it's negative, and the coefficient is 3, so 1 over 3. There we go. All right. For ammonia, there, the all right. For ammonia, it's going to be positive 1 over 2 concentration of change in concentration of ammonia over concentration of time. And that is going to be all of those. Cool. For question 2, this is whenever you're given like this initial rate data, some experimental data. You have different trials or different experiments and the initial rate of these things. To determine the order of each reactant, that's kind of step 1. And really what we're doing here is we're just kind of comparing, if we change the concentration of A, how does that affect the rate? Since we're doing that, we need to make sure that the other thing, B, stays the same. So if I'm trying to figure out the order of A, I need to look through and figure out where is B staying the same and A changing. So 1 and 2 is a good example of that. B is staying the same and A is changing. How is A changing? Well, if I'm going from here to here, I'm multiplying it by 2. What happens to the rate? Going here to here, I'm multiplying it by 2. And the order of the reaction is what is the exponent here to get to this number. And if it's times 2 and times 2, that exponent's going to be 1. This is a first order reaction. Okay. Now let's do B. Same idea. A is staying the same here, and we are times 4 the concentration. And the initial rate doesn't change at all, or we can say it's times 1. So 4 to what power is 1? Well, 0. So we say that B is 0th order. Okay. Now determining the order of the whole reaction, the overall reaction, you just add these boys up. 1, 0, 1 plus 0 is 1. This is going to be first order. Writing the rate law. Anytime you hear write the rate law, reflexively, you should just write out rate equals K, and then the concentrations of your reactants. Concentration of A, concentration of B. And now that we know the order of these reactants, we can just add these exponents in here. We're kind of building this rate law, this formula. So, as a quick reminder, if this is 0, I don't even really need to write it. And I also don't need to write the 1. So this is also an acceptable rate law. All right. Okay. Q3. So question 3, the decomposition of A to B3 is, oh, I missed one. Calculate the rate constant. Once I have the rate constant, rate equals K, concentration of A. Now I can go through and actually plug and chug one of these things. I'm just going to take 2, for example. I'm going to plug in the concentration of A here and the initial rate here, and I should be able to get K out of this. Now, what is it, to actually do the algebra here? We know that would be K equals the rate over concentration of A. And when you do this, you can actually see something that the depending on the order of the reaction, K is going to change. The units of K is going to change. So rate is always going to be molarity per second. And then since this is first order, it's concentration to the first power. We have molarity on bottom. And this means that the units for K are 1 over seconds, or seconds to the negative first power. So there's that. But, hang on, what happens if it's not to the first power? What if instead it's to the 0th power? What units come out if you have a concentration to the 0th power? You don't have any units. Just like if I had A to the 0th power, that's not A anymore, it's 1. The units go away. So there's no units on bottom now, and since there's no units here, K is molar per second. A different unit than if it was first order. In fact, if you see K being molar per second, molar over second, concentration over seconds, then you know automatically, 0th order reaction. If you see K being 1 over seconds, you know, first order. If this is second order now, what happens then? Well, then this would mean molarity squared is on bottom. And if I rearrange all of these boys around, what we end up is 1 per molar second. If you see, or molar to the negative first, seconds to the negative first. If you see this, you can think, second order reaction. And you can keep going if you want to do like to the 3rd power, to the 4th power, so on and so forth. Yep. Dimensional analysis. Wonderful thing. Just basic algebra. All right. So that is that. And you can just plug and chug then at that point of what these guys are. I wish there was like a erase all button on this. One sec, I'm gonna pause. All right, this is better for me now. Okay, so the next one. So the decomposition of A to B3 is second order, with K equals 6.5 times 10 to the negative 5th molar to the negative first, second to the negative first. Here's the thing, they straight up told you it's second order, but you didn't need it because you had the units here. So right off the bat, you can just think, molar to the negative first, second to the negative first, that's going to be second order. Now that we have second order, we can think back and look on your cheat sheet. In fact, let me just get that for you. AP chem constant sheet. And you can look to see which one of these formulas you need. This is the second order one, so this is the formula we're going to be using. Okay, awesome. And all right, so we know that it's 1 over a concentration equals 1 the concentration of A naught minus K, oh I'm sorry, plus KT. Here's the formula, and I have the initial concentration, I have K, I have a time, and all that's left over is A. So I'm going to go through and run through this. So K times T is going to be this K times this T. The thing we have to remember is that this is in minutes, and this is in seconds. So let's go through and multiply this by 60 to get 180 seconds. All right. Now, 6.5 exponent to the negative fifth times 180 is some amount of number. This number actually is, well, no, that's not true. Then we're going to add this to the reciprocal of the initial concentration. Initial concentration is 0.5. Reciprocal of that is 2. So this plus 2 is 2.0117. Okay. So I've taken care of all of this. So we know that the reciprocal of the concentration of A equals this. So to write this, we just need to take the reciprocal of it, and we get 0.597. This makes sense. It went down by a little bit. This K, you probably aren't familiar enough with it now, but this K is actually kind of small, which means looking at this -5 here, I can say, yeah, this is going to be a pretty slow reaction. It's not going to be moving quickly. There we go. So that is going to, that makes sense. That answer makes sense. Okay. Then, actually, if you guys are watching, you guys are probably watching this on Wednesday. You have an assignment that's going to be about four to five, depending on how you want to look at it. Questions that are similar to this, where you need to figure out the order and figure out, use the integrated rate law to determine concentrations. All right, what is the half-life for this reaction? The half-life, again, this is going to be one of those things that are going to be given to you. It's 1 over K concentration of the initial. And then just plug and chug. I mean, we have K, we have that, and you go. It turns out to be something like 30,000 seconds. It's I calculated it today, 8.5 hours. So it's a hefty reaction. My phone is going off. Apologies. There we go. All right. Q4, I'm going to leave this one for you guys to do. It's the same process, though. Q5 is going to be the same process, but instead of looking at the initial concentration at time, instead of that being your X, it's giving you the concentration at that time, and it's asking you how long will it take. So it's asking you to find time. All right. Question 6. For the reaction below, if substance A is disappearing and at a rate of 1.82 times 10 to the negative second molar per second, what is the rate of C appearing? So this is just stoichiometry. You can take this rate and it's A, so 1.82 times 10 to the negative second A, and then do your stoich step. A is on bottom, C is on top. That's 5 over 3, and plug and chug from there. If you're wondering how is this stoichiometry, we've been doing some crazy integral calculus stuff. This is too simple. Well, just remember, if you kind of logic through it, that for every turn of this reaction, I'm losing 3 and gaining 5 of C. I'm losing 3A, gaining 5C. So if I lose 3A per second, how many C per second am I gaining? That's 5 per second. It's that same type of ratio that's going on. Okay. Question 7 is exactly same as before, same as 6. All right, so I'm having trouble with the videos, but it'll be okay. We'll continue on. All right. So I'm gonna go through this a little bit quickly because this is the second time I've been through this. Question 8. This is essentially going backwards. If I give you the rate law, can you tell me what what else is going on here? So here's the rate law. Here's the equation. And here are the, the questions. What's the order of hydrogen peroxide? Well, the order of this is going to be 1 because it is, it's the coefficient's 1. So first order for this one. For iodine, same thing, first order, because it's 1. And then for H+, it is a reactant, but it doesn't show up in the rate law. So you can assume at that point that it's 0th order. So 0th. Overall, 1 and 1 and 0 is 2, second order. All right. Same thing here. This is kind of the reverse of what we talked about before. It gives you the order, second order, and you have concentration increase. So if you calculate this out, this is a times 3.5 increase. So this is a 3 times 3.5 increase. What should happen to the rate? Well, it should go up by a factor of 3.5 squared, which ends up being 2.25. Okay. All right. This is just a more complicated version of question 2. The things you need to remember here is just be aware that, like, if I'm looking for bromate, the order of bromate, make sure that the other two are holding steady, that they're staying the same. All right, so there's that. I'm going to let you guys run through this if you haven't yet. One other thing to be aware of is that they may say express K with the correct units. You can go through like I did before to figure out what the units are. If it's 0th, it's molar per second. If it's first, it's per second. If it's second, it's 1 over molar seconds. Third is going to be 1 over molar squared seconds. Fourth is going to be 1 over molar cubed seconds, and so on and so forth. What's the initial rate of change if the initial concentration of bromine is non-zero? So here's the thing. We haven't gone over this. We'll go over this more when we talk about equilibriums. But go ahead and think about it. What would happen if I had some of this initially, a product initially? What do you think would happen? Think about it. Just think about it. Questions 11. All right, so we're going to go through, talk about CFCs. They're bad for the environment, and this is why they're bad for the environment. Up in the atmosphere, CFCs make free chlorine radicals. These is not Cl2, as you notice. This is just Cl. It's a single atom of chlorine, very reactive. And up there, it actually reacts with ozone with this elementary step. The first thing is write out the overall reaction for this. And to do overall reactions, if it's in the products and reactants, you can cross them out, and you do that. You get ozone plus an oxygen radical creates 2 oxygen gas. And there you go. This is the overall reaction there. What is the catalyst? Remember, a catalyst is something that's there in the beginning. It does stuff in the mechanism and then gets regenerated. So from an outside observer, you can look at this and be like, chlorine's not changing at all. The concentration isn't changing, but it still is needed. So for that, the chlorine is going to be your catalyst. It's something that's there in the beginning and then gets regenerated. Okay. An intermediate is the other side of that coin. It's something that is formed in the reaction and then get used up. So these things that you're crossing out, they're either going to be catalysts or intermediates. Catalysts are there in the beginning and regenerated. Intermediates are created and then destroyed. Okay. Explain how a small amount of CFCs can destroy a large amount of ozone. The reasoning behind this is it gets regenerated. So the chlorine here does this first step and then gets regenerated in the second step. That means that the concentration of chlorine never actually goes down in this reaction. This chlorine radical can go right back and react again with ozone. So this is why a very small amount can cause pretty devastating things to the ozone. As far as what breaks the bond, this is again, you have to read up here, ultraviolet radiation. You can kind of go back to remember what happens whenever a photon or any type of energy radiation hits an electron. What happens to it? It goes up. There's that. Also, ultraviolet radiation. Yeah, that's that. All right. Question 12 is similar to 11, so I'm going to let you go ahead and do that. The big difference here is the slow and fast. You can go through and figure out the overall reaction, catalysts, intermediates, and so on and so forth. But which one of these guys is going to be your rate determining step? What does that mean, rate determining step? So a rate determining step basically means what's taken the most time. Where is all the time in this process actually coming through? If I'm going through and me and little Jimmy are in an assembly line and we're building model trains for Santa's toy shop or something, if he builds an entire train, hands it to me, and I slap a sticker on it and then move forward, it doesn't matter how fast I slap the sticker on, I'm going to be sitting around waiting for another model train to come. It doesn't take long for me to slap a sticker on it. It takes little Jimmy a lot longer to make that model train. So the slow step is going to be your rate determining step. This is the one that actually matters. Okay. Let's look at D. Given an uncatalyzed overall reaction is a slow exothermic reaction. Draw an energy diagram. So it's exothermic. Exothermic means that it starts high, ends low. We are losing energy from the reaction. The energy is leaving the reaction. And then what's this middle part going to look like? So there is 2 steps here. One that's really slow, so it's going to have a very large activation energy. And then one that's fast. It's going to have a little activation energy. And there you go. Here is going to be your exothermic reaction that shows 2 steps. One of them is very slow and has a very large activation energy. If I go through and I'll say blue is going to be my catalyzed reaction. Remember what a catalyst does, like up here, up here, the overall reaction was O3 plus oxygen radical goes to 2O2, right? This could very well be a different mechanism for it, right? This mechanism right here, a oxygen radical could slam into O3 and make 2O2. That's fine. It probably has a very high activation energy in order for this to go through. This chlorine, this mechanism probably has a lot smaller activation energy. It's a different path to get to the same place. So this can, this catalyst can lower that activation energy. So it's saying draw a possible curve for a catalyzed reaction. There we go. We've done it. It's just a smaller activation energy. All right. What does it mean by rate determining step in a reaction mechanism? The slow step takes the longest. Fast steps are usually much faster. And so the total time of the reaction, the total rate of the reaction is determined by the slow step. Again, think of like Jimmy building a model, passes it to me, I slap a sticker on it, and then move on. What is determining the rate of trains being produced? Jimmy. Obviously not me. All right. What is meant by a reaction mechanism? So that's kind of what I meant up here, where we have one potential mechanism with a catalyst, and there's another mechanism where the ozone, O3, and this oxygen radical just slam in together to make the 2O2. So those are two different ways the same reaction can take place. One's a little bit more convoluted, but this one I would have a lower activation energy. It's easier to get over those hills. How are reaction mechanisms determined? Reaction mechanisms are determined by first discovering the rate law. So if I can go through here, and let's assume that this one is the slow step and this is the fast step. Okay, I can go through and find the rate law of O3 plus O goes to 2O2. And if this is the slow step, the rate law is going to just have to do with the concentration of O3. So it may be, first order with O3 and 0th order for oxygen. And if that's the case, we know that oxygen doesn't really do anything in the reaction. It doesn't really affect the rate at all. Think about it like this. Going back to the train example, if I have doesn't matter how many stickers I have. I could have all the stickers in front of me. I could have them all peeled and on my hands, ready to go, to be as quick as possible with my putting the sticker on. It's not going to make us, get more trains out the door. The thing that's going to get us more trains out the door is if Jimmy hurries up and starts getting faster. So that's what a 0th order. I'm the 0th order with slapping a sticker on. The first order though, that's the person, the slow step, the rate determining step. So finding the rate law can help us determine these steps. Okay. All right, we got a complicated energy diagram here. This complicated energy diagram has a couple of things. One, is this going to be endothermic or exothermic? Endothermic or exothermic is the property, the product, the reactants. Here are the products. What is happening here? Is this reaction gaining energy or losing energy? I start here and I'm moving up to here. which means this reaction is gaining energy. Energy is going into this reaction, so it's an endothermic reaction. So endothermic reaction. What are some other things we can tell from this? It's going to have 1 step, 2 step, 3 steps. It's going to have 3 different steps, 3 different elementary steps. And it tells us that right there. All right. So let's go through. Which arrow indicates the activation energy for the first step of the reverse reaction? So if we're going reverse, we're going backwards. So I'm going to start here and then move my way up. This, from the start of the step to the top of the activation energy, is going to be, or top of the hill is going to be your activation energy. So 5 is the activation energy here. Okay. Activation energy for the first step of the forward reaction. Same thing. We start here and we move up to the top of the first step. That's going to be 1. Which arrow indicates the activation energy of the second step? So here's the thing you have to remember. It starts at the beginning of the second step here in the intermediate land, and then move up to the top. So 2 is going to be the one for this one. Which arrow indicates the enthalpy change of the forward? It's going to be 6, where you start here and end here. For the reverse, it's going to also be 6. Start here and here. Which arrow indicates the activation energy of the overall forward reaction? So overall reaction means you start here and then go to the top of the slow step. The slow step being the largest peak here. So then it would be 3. Which step would be the rate determining step? Well, which one of these has the biggest activation energy? Which would be 2. 2 would be the activation energy there, biggest activation energy. So you know that the second step here is going to be your slow step. All right. Draw a dashed line, a possible curve that represents a route for the uncatalyzed overall reaction. Label this on the graph. I don't know what uncatalyzed reaction it is. Let's just assume, basically, it could just be like, one of these activation energies being larger. Something like this. Not the wave, but yeah, there's something. There you go. All right. Would you expect this reaction to take place in a single step or not? So, with this reaction, 4 hydrobromic acids and 1 oxygen molecule. Would this be a single step? If this was a single step, what you're saying is 4 hydrogen bromides and 1 oxygen all slam into each other precisely in the correct orientation with enough force at the same time to make H2O and bromine Br2. 2 of them. So, for funsies, try drawing the Lewis structure of all 5 of these molecules, getting their orientations together to make 2 waters and 2 bromines. It's going to be hard. It's going to be almost impossible. And the fact that 5 things all hitting at the same time is also going to be pretty hard. So you can say that no, this is not going to be a single step reaction. It's going to be multiple steps. Maybe 2 of the hydrogen bromines are going to slam into each other, or maybe the oxygen and the hydrobromic acid is going to slam into each other. Yeah, here is the proposed mechanism for it. So this is the proposed mechanism. First step, hydrobromic acid and oxygen slam together to make this intermediate. Same thing here. Hydrobromic acid slams into it again to make another weird intermediate. Then 2 more hydrobromic acids hit these weird intermediates to make that. This is weird to me. The fact that 2, 2, 2, 2. Oh, okay. All right. So, in all actuality, this is probably, you may notice something weird about this. I didn't notice it until just now, that this is all 2, 2, 2, and 2. Do you really think we have 4 things all slamming into each other? Or could I reduce this down to make it 1, 1, 1, and 1? And then it just happens twice. Don't worry about that. You don't have to worry about that. That was just a cool thing I noticed. All right. Identify the 2 intermediates. The 2 intermediates, what you can do is the same thing as before. If it's on the reactants and products, they're going to cancel. So there's one intermediate, the Huber, HOOBR, and then these 2 HOBRs. And there you go. So if a catalyst is discovered for step 3, will this affect the rate? So in step 3, if the company that makes these trains comes up to me and says, Tony, you need to put more stickers on faster. We bought you a machine to help put stickers on, a little handgun to put stickers on. Would that help? No. I'm not the thing that's slowing us down. You know, Jimmy over there is the one making the trains. So he is the one that needs the catalyst. He's the one that needs to lower his activation energy to speed him up. So step 1 would do that. Which step has the greatest activation energy? That would be the slow step. How many peaks would this have? 1, 2, 3. 3 peaks because of 3 steps. Which step is the rate determining step? It's the slow step. In order to have successful collisions, colliding particles must have proper amount of energy and proper orientation. Sure. All right. And then draw energy diagram which shows the shape of the curve. So we know that this thing is exothermic. It is losing energy. So once on the reactants are going to be higher than the products. Then the first step is going to be slow. So this is going to be a big activation energy. Okay. And then we're going to have 2 more activation energies that's a little bit slower. And then it's going to come back down. All right. That's that. I'm going to call it here. There's actually more that I didn't give you. I think I may save this for a different video. 1 or 2 more of these for a different video. All right. See you guys later.